All right, so our next speaker is Ricardo Henriques from IGC in Lisbon, Portugal. So Ricardo is going to slowly get set up. But Ricardo and his group uses optical and computational biophysics to study cell biology and host-pathogen interaction. But his group is also very famous for developing very easy-to-use image analysis tools. So I'm sure that many of you have heard of SRRF, NanoJ platform, or Squirrel. And I have to say, I'm really delighted that Ricardo could be here today. So Ricardo and I actually have been working together for quite a while, maybe about 4 years now, collaborating on various projects. But actually, yesterday was the first time that I had the chance to meet Ricardo in person. We've been collaborating online for so long. So Ricardo's title is Open Technology for Super Resolution and Machine Learning Enable Live-Cell Biology. I really look forward to your talk, Ricardo. Please take it away.
Thank you so much, Guillaume. And I can't really say how happy I am to get a chance to finally meet you. There was COVID in between, and we've tried so many times. All right, so I'm going to give you a little bit an overview of some of the latest technology we've created in the lab. And I wanted to really start by saying that everything that you're going to see is thanks to the lab members that pioneered it. And it's quite special to me, this meeting, because there's a couple of alumni from the lab that are here. So David and Karen, I miss you every day. And it's really joyful to also have had a chance to meet them again. So we've created a library of many methods for microscopy. Most of them are computational in nature, and most of them are dedicated to super-resolution microscopy. And I'm going to just touch on 3 today. I'm going to tell you about eSRRF, the new evolution of SRRF. And I'm going to also tell you a little bit about what we've been doing with machine learning also. So let me start with eSRRF. So what you're seeing here is a typical single molecule causation microscopy dataset. In this case, a STORM dataset. And it's very similar to what you want to get on a microscope, because you see individual molecules blinking there, which means that you can use a filter to localize those individual molecules. But the problem with this also is that you're spreading information over a large amount of time. You're pretty much needing to acquire about 10,000 to 100,000 frames to actually recapitulate most of the molecules that exist in the sample that might then blink during that time. This has a problem, right? Because if you're actually trying to do live-cell imaging, on one side, you're spreading information over time, which means that your temporal resolution is quite low. On the other side, you're pretty much killing the cell, right? There's so much photo damage that you're imposing to the cells because you're pumping considerable amounts of illumination to actually get molecules to blink that cells don't really survive for long. So this is something that we wanted to play with and to try to improve in the context of single molecule causation microscopy. So this is a little bit of what happens once you decrease illumination power, right? So it happens that most fluorophores that we use in single molecule, their blinking photophysics are modulated by the illumination that you put in. So as you decrease illumination power, what you get is something like this, right? Where you don't really clearly see individual molecules blinking anymore. And if you use a filter to try to detect individual molecules, it doesn't do a good job, right? That's what you have here from the results from the filter. And then you kind of notice that there's a lot of filaments that disappear that should exist there. So that was the reason why we wanted to actually try to build a new computational methods that would allow us still to extract single molecule information from the low illumination datasets that you see there at the bottom. And for that, in 2016, we've developed SRRF. And SRRF tries to pretty much extract super-resolution from datasets like this. What you're seeing here, by the way, is just 100 frames that I'm cycling over and over. Those 100 frames were acquired in 1 second. And I'm using 40 milliwatts per square centimeter to illuminate that dataset. And that's about 1 million-fold less illumination than what you use on a typical STORM acquisition, by the way. So SRRF pretty much works on two parts. It assumes that there is no such thing as a perfect fluorophore, so the fluorophore emission will always oscillate in some manner. And if the fluorophore oscillations happens in some manner, there's going to be moments in time and space where a fluorophore will emit slightly brighter than any other fluorophore in its vicinity. So if that is true, we can actually use a mathematical transform, which is a radial symmetry detection transform, that tries to pinpoint that there is something that looks like a fluorophore actively emitting in a moment in space that is distinguishable from anything in the vicinity. And the radial symmetry actually does something really cool, because instead of having a PSF model that you fit into your data, what he actually does is just picks up on the fact that most as Stefan likes to call it now, diffraction blobs, have a radial symmetry attached to it, right? And where you have the highest point of radial symmetry is perfectly on where you would expect to be the center of that diffraction-limited blob. So if I apply this transform to the data that you see there, which is just trying to pinpoint where you have points in space with the high degree of radial symmetry, what you get is this, right? And here you can already match some of those high-intensity peaks to the likely presence of fluorophores, but there's also quite a bit of false positives, because even noise, by its completely stochastic nature, from time to time will have some degree of radial symmetry attached to it, which is the reason why, for example, you see fluctuations there on the background. So we have to get rid of that, right? We need to then improve these maps to really improve, to only get intensity where there's a considerable likelihood of a fluorophore existing there. For that, we borrow concepts behind SOFI, where SOFI actually is really good at doing that. Because what happens here is that noise is is highly uncorrelated in time, while fluorophores have a pattern to the way that they oscillate. So if we just start projecting temporal correlations on the data that you see there, what happens is that we bring back where you actually have oscillations that are correlated, therefore the structure where fluorophores exist, and anything that is uncorrelated gets put down on the data. All right, so those are the basic principles behind SRRF. And just to give you a sense of it, so here's a wide field image, and if we process this wide field image with, and this is about 1,000 frames that we're going to analyze, this is what you get with SRRF. So you have a resolution enhancement, but in reality, also, there are imperfections on what SRRF is doing. And now I'm just going to briefly show you the new version of SRRF that we came out about a month ago, maybe. And this is what you get out of it, right? And I'll tell you what is the trick behind it, just to give you a comparison between the two. So there's a considerable quality enhancement on eSRRF. And that comes for multiple reasons. One of them is we improve the mathematical principles behind it. You can read it a little bit about it on the publication. But perhaps the most important thing is that the algorithm is data-driven. So what that means is that it actually studies the data to self-optimize itself to find exactly what are the optimal parameters by which it should analyze the data. And you're seeing a little bit of what the algorithm is doing here, right? What it's going through is it's constantly calculating resolution maps, which are calculated by FRCs, are constantly calculating quality metrics, which are calculated through the Squirrel algorithm that we created a few years back. And it's also looking at how much motility the data has, because it works on the assumption that fluorophores are oscillating, but having almost no motion on the data. And with that, it means that it's also finding exactly what are the constraints of the parameters that it should use to then make that super resolution estimation. So to give you a little bit of comparison, so you can see on the bottom column line there, the error maps, for example, for eSRRF, we have a considerable improvement over SRRF. SOFI is a great algorithm. Also, we think that in many conditions we get much better quality than SOFI, and we have a comparison with HAWK, with a maximum likelihood estimator also. And because it's purely computational, of course, one of the beauties of this is that you can pretty much get eSRRF to work on most microscopes. as long as you obey some basic conditions. The key condition here is Nyquist sampling, both in space and time for those fluctuations and for a structure. So you still need high NA objectives. But for example, we can get it to work on the lattice light sheet, on spin disks, and almost any camera-based microscopes. It will work on a laser scanning of focal, but it's not the optimal way to run it. It works better on camera-based systems. And one extra thing that we actually did is we implemented 3D, and the way that we do 3D is actually with a multifocus device. You heard about multifocus devices a little bit yesterday from Florian. In this case, we partnered with Musa Mhlanga, who has a multifocus system running at Institut Curie. And with that, we were actually able to instance the mathematics of SRRF to work in full 3D. Because we need to have all the different Z points acquired simultaneously for it to work in 3D. That's possible with the multifocus device. And that means that by applying eSRRF, now we get full 3D volume super resolution enhancements on the data. And we can do it live, right? Which is one of the good benefits of doing it. So what you're seeing there is 1 volume per second on the movie that you have on the right. So that's what I wanted to tell you about eSRRF. Check it out, fully open source, runs on Fiji. We provide data to tests, use your own data also, and enjoy it. Now I wanted to switch gears a little bit and also tell you about what we're doing with machine learning. And this is actually a great pleasure because I have Guillaume sitting close to me, and he's fully my partner in crime in the development of what you're going to see next. So one of the reasons why I personally became really interested in deep learning was because in recent years, we quickly realized that for denoising, machine learning is beating any other previous algorithm we've ever developed. And because we work on super resolution, and particularly Live-Cell super resolution, acquiring data at low illumination is really important for us to really be able to follow biological processes for long periods of time. So this opens the door for us to image for much longer, relying heavily on the denoising to then get back the data that we want. So this is what got me interested in machine learning. But one of the things that we quickly realized also is that it's not that easy to use machine learning. And to explain why, I'm going to tell you a little bit about how it works in the context that we use it, by the way. This is often the type of machine learning that you use in microscopy. And to explain a little bit how it works, I'm going just to tell you how is a classical image analysis algorithm. There, what you have is you have some kind of input, an image, for example, and then you have an already formalized algorithm. So someone developed that code that takes a few assumptions. You, as a user of that interface, of that code, of that plugin in ImageJ, take some educated guesses on parameters on that algorithm, and then that generates an output image. In this case, it would be a pre-formalized denoising algorithm where you give it the noise image and it spits out a denoised image. So with deep learning algorithms, typically, what you do is you actually start by showing a neural network examples of inputs and output image, right? And what happens is that network is not well defined yet. Its internal structure and its internal parameters are still free. And what you actually ask to do is you ask the neural network to self-optimize, to train. And pretty much you're saying, can you find optimal parameters within your internal structure by which you find a way to transform the image that you see on the left into the images that you see on the right, right? So it's a little bit similar to you showing example images to a kid of a duck, and then at the end you ask the kids to draw the duck, and the kid will try to base its best capacity to draw that duck. So that means that the neural network goes through this optimization procedure where you show it a lot of data and it learns to its best capacity to transform the data that exists on the left to the data that exists on the right. The optimizer will converge, and at some point it will say, I can't converge anymore, therefore you have a trained network. And at that stage you can give it an input image and it will create a prediction which will be your output image, right? Here's the beauty of it. Here's what gets me awake at night, which is what I'm showing you. The neural network knows nothing about denoising. I gave it no conception of what are the physical principles behind denoising. The only thing the neural network is doing is trying to its best capacity to transform the image that exists on the left to the image that exists on the right. So that means that the same type of neural network, if I gave it a non-annotated image, an annotated image, the same neural network would try to its best capacity to learn how to annotate its image. If I showed it a low-resolution image on the left and a high-resolution image on the right, it would learn in its best capacity to make a prediction on how to improve resolution on images. So it's not task-dependent, it's training-dependent. And that's really beautiful. It has its downside because, the training data really needs to encapsulate any future data that you want to present it. But it's really amazing in that perspective, right? Here's something really naive that just learns from the data how to make a prediction. Of course, this is a problem, right? You need massive amount of training data for it to start doing a good job. Well, this is what I would say yesterday until I saw Anna's talk. So there's a few things that you can improve on from that perspective. So we wanted to make these easier for everyone to use. Because on one side, you have this idea that you need training data or you need pre-trained models that are able to encapsulate the experiments that you want to do. And I showed you some solutions for that, right? There's the model zoos where you can now start picking up models and do transfer learning with them. And then there's the other perspective, which is you need access to high-powered GPUs to run these machine learning tasks, and you need to learn how to do it. So Guillaume and I did not meet on an ELMI meeting, but we met on Twitter, I think, maybe, yeah. And we didn't sit down, but we zoomed out a few times. And we came out with this idea of trying to make a platform which would make it easy for everyone to do training with machine learning. And that became zero-cost deep learning for microscopy. So what is it? The only thing that you need to use it is actually a browser. Everything is done on the cloud. Well, you need a browser and you need some data, right? And with that, what you're able to do is with the browser and the data, you're able to push this to Google Drive. One of the benefits of Google Drive is you can actually have a free account, so no cost so far. And it also happens that Google has a free service called Google Colab that gives you free access to a GPU. Now, the thing about that GPU is that it's a GPU that is already within the expectations of machine learning. So it has the GPU memory and the performance that you can generally use for a large number of different tasks that you might want to do with machine learning. So pretty much what we did is we generated a set of Google Colab notebooks that presents an extremely easy-to-use graphical interface where you aren't expected to have any coding experience. So the only thing that you have to do is to interact with that interface. And next to that interface, you have full tutorials explaining exactly what each parameter you're playing with actually does. So it's actually an outstanding resource for you to learn how to use machine learning. So with that, that means that you can do network training on your data. If you don't have data, by the way, we also provide example data for everything that we do. So you can immediately start the computer, grab data, and try it out, learn how to use machine learning, and learn how to use some of the tasks we have implemented. So you get network training, prediction, and then you can obviously pull back the data out of it. So what can you do with this? Oh, and by the way, so it's fully free, right? Everything, all the services and everything that you see there is fully open source, fully free. You can use it immediately if you have a laptop with you. It really is meant for non-experts, so you don't need any coding experience. And we actually spent quite a bit of time implementing quality control so that you understand to what degree can you trust the data that you're getting from the machine learning predictions. So, some examples of what you can get with this. I'm just going to go through some of the networks that we've implemented. And by the way, many of these networks are developed by other labs. The only thing that we did is we re-implemented those networks into the zero-cost deep learning for microscopy platform. So you're seeing here segmentation network like a UNet, a Stardust, and now we're going to shift into classification. In this case, for example, we were phenotyping cells that you had on that field of view, noise to void from the Frey-Wilk lab, which the noise is data. CARE, one of the first machine learning algorithms dedicated for microscopy that works extremely well. DeepStorm, that's the single molecule detection with machine learning. FNet, one of my favorites, where you go cross-modality predictions. In that case, we had a bright field image, and we're able to predict a fluorescence image from that bright field image. CycleGAN, in this case, predicting supersolution images, for example. You can see all those tasks and all the examples that we have on the GitHub website. And just to wrap it up, recently, we've readapted a few notebooks that we had on zero cost, particularly dedicating them for bacterial imaging. A lot of the neural networks and models that you see out there have been developed for eukaryotic cells. So that allows us to develop deep packs. And you see most of the tasks and a few more that we've added to zero cost to actually directly process data from bacteria. And you have a few fascinating things, like, for example, phenotypic classifications for drug discovery, which is what you're seeing here, for example, where we pick up on morphological features that change on bacteria, or even divisions progression when they are exposed to different drugs. And with that, I think I am almost done. Artificial labeling, always one of my favorites. And I showed you a little bit of the lab. There's a few collaborators that have tremendously helped us getting here. And I am happy to take any questions you might have.
Thank you so much, Ricardo, for the amazing talk. So we have time for questions from the audience. So there's at least one question here in the middle. So, sorry, could you just wait for the microphone, because otherwise we can't hear you so well, and then the online audience cannot hear you. Thank you so much.
Thank you, Ricardo. Thank you very much. I have two questions. First, about applicability of SRRF on Airiscan. What to calculate first, ARI processing or SRRF? And second question about live imaging application. Did you think about developing on something like a rolling frame, that not 100 frames, 100 frames? Yeah, okay, thank you.
So the great two questions. For the Airiscan, the one of the things, so SRRF assumes that it's getting a raw image as its input, because it makes some assumptions about the type of noise that that image has. So that means that, for example, if there's any post-processing on the data that you acquire on your system, being it a deconvolved image or being some of the procedures that the Airiscan have, that might impose some anomalies into SRRF because the noise features that he's expecting might have changed. So I would be a little bit careful. I'm not saying don't do it. I would just be a bit careful, and I'm unsure how good the output would be at the end. Now, the rolling frames. Yes, the eSRRF algorithm, we've implemented it. And with that means that, for example, typically you could have your 100 frames, but then you're just rolling one frame at a time to create multiple reconstructions also.
Thank you very much.
My pleasure.
So the next question is over there, Ricardo.
Hi, Ricardo.
Hi. Sorry.
Very nice talk about the deep learning. So do you offer in this cloud-based solution some way to share trained networks? Because obviously if we start to use it, I mean, hopefully people will generate a lot of well-trained or more or less well-trained networks. And of course it would make sense to share it somehow. I mean, given that there is readiness. So do you have some thoughts about how that should work or how one could do that?
Yes. So on pure zero cost, we do not. But in the bioimage model zoo, we do. So the bioimage model zoo ends up being a repository for all the notebooks and all the models that people are training. So that means that you can, and they're fully compatible with zero cost. So that means that you have bioimage model zoo as being kind of the Google of deep learning, where you pick up all the resources there. And then zero cost is one of the tool sets that you have there, and it's compatible, cross-compatible with models, and you can even, those models would then be runnable on Fiji, Elastic, and many other interfaces beyond zero cost also.
All right, we have time for one last quick question from over here.
Thank you. Thanks for the talk. I'm always worried, as I'm head of a facility, to direct my users to certain tool that they could use for analysis.
Yes.
What I worry most about AI, and machine learning in particular, that they forget to control or do some quality control after some time. You have to always go back and check whether this is correct or not. So what do you think would be the best way to make a user who would rely on the algorithm to use it? And then how do we control that they are going to check systematically that the output is correct and there is nothing, and they do retrain? And I'm really worried about this part.
That's a very good question. And unfortunately, the problem is that there is the quality control on most algorithms, including machine learning, is not a binary decision. You will have some ranking. It will tell you, for example, it's 90% accurate. But you still have to evaluate what that means. Is 90% good enough, or is that 90% actually just representative of all the noise that you have on the data? And the really interesting things happen in the 10% that algorithm is not able to do correctly. So for all things that I showed you, including SRRF, there needs to be cross-validation with another method. And I believe that is true for almost anything that you do with machine learning. You need to have insight from a completely different perspective to validate what you have there. Now, it's really important to train users to actually understand what is quality control, how they can use those quality control metrics to their benefit. And there are algorithms that can classify the quality control. And you can always ask what's the result of, what's the error map that they have from those predictions, which, by the way, with eSRRF, you can also get error maps. You can also ask, show me the error map so that I know where the artifacts are and if there's artifacts on the data or not. So at the end of the day, even for everything that we do with super resolution, I always go to EM microscope to acquire that data also to visualize what's going on there. So these are very powerful tools, but as with anything in biology, hey, we've been using Western blots for decades, and we use it every day, but on the back of your mind, you know how much artifactual they are also, right? But it just happens that because we've been using it for decades, we know how to deal with those artifacts. The same thing happens here in machine learning. You always expect defects on the data. That's true for super resolution, for machine learning, and etc. Then it's a question just how can you validate them and how you can interpret them, because there is important data among those defects that exist always there. Did I answer your question? You can always have a coffee afterwards if you want.
All right, so join me in thanking Ricardo for an amazing talk.